Hello, everybody. I am Bega Clavero, and I'm a passive house consultant at Ingeniería Progetic, and I'm going to show you an optimization study that we have developed for the industrial kitchens in passive house elderly homes, and we have a particular project that we're working on here in Barcelona. Well, you can see here some data of the members of the team, as well as some pictures of the site. The Mirador de Gracia project is a new project that is being built today, and it will be certified as a Passive House Classic. It's a building that has two bodies, following the geography in the area, which is on a mountainside. The southern body has one underground floor and three above. And the northern one, which you can see in the picture at the back, has one underground and seven above. Some of them are semi-buried, and that's where you find all the services for the residents, the coffee shop, the industrial kitchen that we'll talk about, the gym, the theatre room, and others, and the upper floors that have more rooms. We need to take into account that an elderly home is a building that's rather particular because it has a high occupancy level throughout the year. And to this, we have to add many other services that a residential building would not have, such as an industrial kitchen, an industrial laundry, a gym, or a theatre or AV room. That is to say, equipments, and many of them that are going to consume a lot of energy. When we face this challenge of including an industrial kitchen in a passive house building of this size, we started to think on what had to be taken into account and where we could find some problems. Because in the end, these kitchens have high power equipment and they need a high flow air extraction system, and this is translated into high energy consumption and an important production or generation of residual heat. So what have we focused on? So when we talk about this level of flow, we have equipment that is producing flues, and therefore you need a high extraction flow, and this clashes a little bit with a balanced ventilation system that the standard requires. The ventilation system of an industrial kitchen in this building is going to be totally independent from the rest of the building. But even so, it has to be balanced. And not only when it comes to extraction, we also have gas-supplied equipment, usually in a kitchen, and gas means that you need certain vents for ventilation purposes as required by the rules, which clashes with the airtightness of passive house buildings, and we have to see how we're going to solve this problem. Equipment also consumes a lot of electricity, and all of this has to be included in the calculation of the primary energy demand. Therefore, we have to contain this and try to find the most efficient equipments possible. And finally, we have an important level of heat generation because the equipment is focused to produce heat for cooking, and their mere operation already produces residual heat, and therefore they're going to produce additional internal gains. When you study the initial kitchen plan, this is the kitchen that's on the second floor in the first building and includes a storage area with fridges and freezers, an area for food preparation, another one for cooking of food, and another area where the laundry is located. And you can also see that we have three exhaust hoods, one for the laundry area, one for the oven, and another one for the cooktop. This is the only area where you have a certain air inlet, which is that green duct that you see on the plan. The others would only be exhaust hoods. And then we also have the small yard that is connected to the upper part where the fans are installed for air extraction. So we have 3 exhaust hoods where only one includes air injection. So as you can see, this is the final result of the ventilation system, but the flows are not balanced. In fact, even more so, they're very imbalanced. We also have provided for additional equipment. As you can see, there's equipment that has to do with food, cooking, that would require a gas installation, so there's going to be combustion. So after having carried out this study, we focused on the issues that we believed could be problematic and tried to find proposals to create an energy efficient kitchen that is also healthy. So let's start with fume extraction. The first thing we tried to do was to adjust the inflow with the extraction flow in order to balance the flow, and we did it installing compensating exhaust hoods. The compensating exhaust hood brings air from outside, injecting air, and which is balanced with vapor and flue extraction, and this way we were able to balance the flows. In fact, including this air makes it better to do away with the fumes and vapors. So for the same effect, we needed less flow. So flow levels were lower. And the reduction could be up to 27% less. So it means that energy consumption of the exhaust hood is also lower. The operation of a compensating exhaust hood is as follows. I think you can see it in this outline. The blue arrows are the air that's injected into the system that comes out through a series of grills in an angle downwards. And the outside of the hood itself, whereas the extraction happens within the exhaust hood structure, producing a semicircular sweeping movement. And we recommend these traditional compensating hoods instead of induction exhaust hoods. Induction exhaust hoods are also compensating, but the air injection also happens within the structure of the hood itself. So the sweeping movement is much lower, and therefore they're not as efficient from an energy standpoint. They require more flow for the same effect, and therefore there is more consumption of energy than in traditional compensating exhaust hoods. Another important issue that struck us as interesting is that you can optimize the operation of the exhaust hood if you change the cooktop placing. So if you install the cooktop and the exhaust hood leaning against a wall instead of in an island concept distribution, which is common in this type of kitchen, so the flow can be reduced up to 30%. And if you reduce the distance between the cooktop and the exhaust hood, which is usually 1.60 meters down to 1.20 meters, so it's still comfortable, the flow will also go down 20%. So if we reduce flows, then we're reducing energy consumption. I'm going to give you an example. And we actually tested it with the different sizes of the exhaust hoods of our project. We calculated the flows for the 2 types of installation, so whether it is an island or leaning against a wall. As you can see, the difference in flow values is important. When it leans against the wall, you need 30% less flow to obtain the same result. This means that you're reducing fan consumption very much. Another very important thing to take into account is flow control. If we're regulating the exhaust hood control depending on cooking requirements, and we don't operate it manually with an on-off system or with only 2 speeds, we can reduce consumption levels very much. And in order to do this, we need a flow self-regulation system That would include a temperature probe, a smoke opacity sensor that would be operating with a frequency converter. You can see the outline here. These types of probes and sensors are included in the hood structure, and it's easy to clean and maintain them. And if you regulate the flow, you would be able to reduce it very much so. And you can see here how the system operates. When the temperature probe detects heat because you're cooking and the temperature increases, or detects the opacity, that is to say that there is smoke, then a signal is sent to the frequency converter, which sends a signal to vary the speed of the fans that would be controlling the flow. And on this chart, you can see how an exhaust hood operates with self-regulation sensors throughout a day. And as you can see, it has been fixed for fans to work at 40% of their speed. But there are certain peaks where they're operating up to 100% at certain times of the day, which have been times when you've needed to extract these smokes and smells more. And we're finally talking about what to do with heat recovery. As this is an independent system, we assessed the impact of heat recovery on the heating requirements of the building at large. And you can see here that we have the results of heating requirements without applying heat recovery in the ventilation system of the kitchen. And here we have the same heating demand, but with heat recovery in the kitchen ventilation system. The two resulting values are under the parameter that we have in the standard, that would be 15 kilowatts hour per square meter year. Therefore, we decided to rule out its installation, and we would be saving installation costs and maintenance costs, and we were also making maintenance tasks much easier. It's important to point out that we've done this because we have a warm climate in Barcelona, and it's not necessary. But in other parts of Spain, the recovery process would be absolutely essential because we're talking about important levels of airflow, and it would be an essential practice to carry out. Let's change topics completely. Let's go to laundry centers. They are used intensively on a daily basis, which lead to high energy consumption levels, and they also require the extraction of vapors from laundry activities, and that's why an exhaust hood is also necessary in the laundry room. Laundry centers are usually huge, and they automate the washing and drying system, and you can see they usually have a series of modules, and to include them in a passive house kitchen, we recommend the following. You have to look for equipment that has a heat recovery of wastewater. What does this mean? It means that the water that has been used during the washing process can be recirculated and preheat the rinsing water. That way we would be reducing energy consumption by 20%. And they should also have heat recovery of the vapor produced during the washing process, and that is done with a heating pump that condensates this vapor, and this way we are eliminating the third exhaust hood, which would be the vapor extractor. So we're reducing the ventilation flow that is required in our kitchen, and we are achieving an important energy saving. Another alternative, which is also extremely interesting to think about, particularly for professional, medium-sized or small kitchens, which are used sporadically and not 7 days a week, would be hood-type dishwashers. They're simpler pieces of equipment, and there are models that also include heat recovery from wastewater as well as the vapors produced during the washing cycle, and as they're simpler to use, and they don't have so many functions, they are improving the electric potential. On the other hand, it's also true that they're more labor intensive. That's why we've recommended them for smaller kitchens. In our case, we weighed this opportunity, but comfort and efficiency in the laundry process took over because they have to serve 3 warm meals a day. Another issue that we covered at the beginning of the presentation was what happens with the gas installation. The fact that we have ruled it out at the Mirador de Gracia Center makes it compatible with the standard requirements. So we've made airtightness of the building a reality. We've reduced infiltrations of non-tempered air, that is to say, as we don't need a gas installation with live fire that requires constant ventilation, we can remove these grills and reach the standards parameters for infiltration, which are very low levels, because it's extremely important to pass the test, and it's famous. And we also improved climate control equipment performance and workers' comfort, because they won't have undesired drafts and non-tempered air. We also improved the quality of the interior atmosphere because there is no combustion. And as we work with induction, we're also reducing the emission of fine particles in the kitchen. And this is also an improvement in workers' health. And finally, as we don't have gas equipment and we have replaced them for electrical equipment, well, we have a limited and non-renewable energy source. Electricity means that it can be generated with renewables such as PV, which could be in the same building or outside elsewhere. As far as electric equipment is concerned, we asked manufacturers for advice. They've been very helpful and replaced the gas equipment we talked about at the beginning of my presentation for electric equipment with similar features. It is important to note that we worked with a company that manages the kitchens of other homes of the same group. If they had any problems of changing from gas to induction or from electric to gas, and they said they had no problems whatsoever, and we could do what we considered more appropriate. They didn't mind. And this is important because everybody feels comfortable working with equipment that is slightly different. This change had effects. And when it comes to primary energy demand, it went down 4%. It may not seem a lot at the beginning, but what have we done? In the end, we've replaced 6 or 7 pieces of equipment that were gas supplied to be electricity supplied. And this minor change that is neither removing nor replacing nor making more expensive or cheaper, with this simple change, we have reduced to a certain extent the renewable primary energy demand, which is very important. On the contrary, we did increase CO2 emissions. So you may say a priori that this is not good, but you have to see it within a context. This is a picture of what is happening in 2020. But it is true that with CO2 emissions, with electric equipments, may go down in the future. What do I mean by this? It depends on the emission factor of the energy. Gas emission factor is going to be a constant value, whereas that of electricity will change depending on how electricity is generated. And it is going to be lower every year as renewables are included in electricity production in our country. We can see it here. The energy mix of the 5 years is plotted here on the dotted line, which shows you the CO2 emissions factor has gone down from 0.32 in 2008 to 0.28 tons of CO2 per megawatt hour in 2017. So the trend is for this increase to go down. And we would finally like to show you the primary energy study that we've carried out during the Passivhaus consultancy process. This is the most limiting parameter, and it's very difficult to include in buildings like this with high occupancy rates, and which include so many services. So refrigeration and electricity represent 70% of primary energy consumption. And we subdivide these 4 groups in smaller ones. We will see that the ones that consume more primary energy are climate control, such as heating pumps, ventilation, and lighting. And we also have to point out that we have been working and focusing on the facilities that had higher consumption levels. So after this huge design effort that we've carried out in the kitchen, we've seen a multiplying effect in other areas because it only represents 7% of total consumption. I'd also like to explain how we've included the equipment of PHPP calculations because the equipment's power changes throughout the day. So we have foreseen working hours and power levels within those working hours throughout the day. We've calculated a weighted power value and introduced it in the PHPP. You can see here the table and the power values. And to conclude, I'd like to say that we had clear objectives, which were to reduce primary energy consumption, to reduce internal gains, and improve the health, comfort, and hygiene of workers in the kitchen, and to abide by the standards and reduce the demands for refrigeration, which can always create problems in a warm climate. How have we achieved these goals? We've reduced the ventilation flow within the regulations and compensated in the kitchen injection as well as extraction. We have a compensating hood, exhaust hood, and you have to locate the cooktop leaning against a wall and lower the installation of the exhaust hood. We have included laundry equipment for heat recovery of steam and wastewater, so we've been able to not install one of the exhaust hoods, and we don't have gas installation and installed electric equipment, improving the demand of primary energy. And that is all. Thank you very much for your attention. I would also like to thank the involvement of my colleague Oliver Stiles and the manufacturers and commercial companies that have worked closely with us, and I do hope you enjoy the rest of the conference. Thank you.